When your boat comes back to the wharf after a trip, there'll be two main things that will affect the size of the fish you're about to sell. These are fish availability and gear selectivity. Obviously the quality of the skipper has an effect too, because their decisions as to where to fish and how deep to fish will also affect what gets caught. But we might leave that for another DVD series. Referring back to our diagram, we're now going to look at fish availability and how the selectivity of our fishing gear affects what size fish you catch. Then we're going to look at how these two things affect the information being collected. Fish availability refers to which fish are available in the area of fishing. Put simply, if fish aren't there, you can't catch them. That's availability. There are many examples of this in fishing, so let's hear again from our case study fishermen.
They usually start March, April, May right through to late July. Or it has been this year. We sort of had an early start and we're still going now. It's the 12th of June now. We've got about a month left. There's still plenty of fish coming through from South Australia type thing, you know.
Gemfish are a good example of availability. During the winter months, large spawning gemfish are travelling up the east coast at a very specific depth as part of their breeding cycle. This makes them very easy to catch, or very available if you know where to look and what to do. Other times of the year that you can't find them, they have low availability. So, how do scientists deal with availability? Because the size and type of fish you can catch change over space and time, the best way to deal with availability is to collect samples from broad areas of the fishery over a long time period. By doing this, we get an understanding of where and when fish become available to different gear types. The type and size of gear used on boats obviously plays a big part in what fish are being caught. Not only is the species being affected by gear, but also the size of the fish. So, in essence, fishing gear is selective in the size of fish it catches. This is all pretty obvious to fishermen, but it can create complications for scientists when working with information collected from a fisherman's catch. Ideally, scientists want to measure the length and age of the fish population in the water. But because fishing gear is selective, scientists don't get to see the full size range of fish. For example, in a trawl, they might not get to see as many of the small fish as are really out there because they escape through the meshes of the trawl nets. There may not be as many large gummy sharks in catches from gill nets because bigger sharks tend to bounce off the meshes. To get a more accurate picture of fish populations, scientists take into account gear selectivity and adjust fish measurement counts taken from the catch accordingly. In this way, scientists use information that is easily measured to estimate the population that they can't see.
An important thing you need to know when you're comparing what catches are compared to the population of fish in the water is that each fishing gear has its own selectivity, the size range of fish it catches, and this needs to be taken into account when you're running an assessment. For instance, gears might have a minimum mesh size or might have a maximum size, which prevents small fish getting caught in that gear. Now, when you're doing a stock assessment, you need to take that into account and allow for that selectivity of the gear in understanding the growth and size structure of the fish population.
Let's have a look at our case study fish and see how fishing gear selectivity affects the size of the catch.
The escape hatch is to let the undersized crays out, and it works. It's like when we do the tag work, we close all the escape gaps up because they want to measure the whole sort of cross-section of the population, and it's amazing the difference it makes when you actually close the gaps up as to how many fish you get.
We've gone to 95 single braid cod end, and we let a lot of fish out, well, I believe. It used to be 90 and now it's gone to 95, and I think we let a lot of the little ones go, and you don't really want to catch them anyway.
Very small tiger flathead that enter a net can easily pass straight through the cod end. As they get bigger, the chance of them getting through the cod end gets smaller. Looking at it the other way, The bigger the tiger flathead, the more chance of it getting caught. This doesn't mean, however, that there is a definite knife-edge size cutoff. So for example, all tiger flathead from 30 centimetres up get caught. It's a percentage game. Some 30 centimetre tiger flatheads will get caught and some will escape through the net. Scientists describe this with something called L50. L50 is the fish length at which 50% of fish get caught in the gear and 50% get away. So for example, with tiger flathead, as they grow, the chance of being caught increases. We can use our measuring board again to represent how this works. When fish are small, there's only a small chance of them being caught. When they get to a length of about 30 centimetres, they have a 50% chance of getting caught if they enter Wayne's Danish seine net. In other words, half the fish of this length get caught and half escape. By about 35 centimetres, nearly 100% of tiger flathead that enter the net are caught. How do scientists measure selectivity? Well, the stock assessment model usually does that for them, but it can be measured through experiments on fishing gear. Using gill nets as an example, scientists went out on a shark boat with 2, 3, 4, 5, 6, 7 and 8-inch net and measured the sizes of all sharks caught in each of the nets. The 2-inch net showed how many really small sharks were in the population, while the 8-inch net showed how many really big sharks were there. From this information, the scientists could work out what a 6-inch mesh wasn't catching and therefore determine its selectivity. A similar process can be used to determine hook selectivity. Trawl selectivity can be worked out a bit differently. Because most of the larger fish eventually tire and get caught by the trawl, we are more interested in the small fish that can escape through the trawl net. To measure selectivity in this instance, we surround the commercial cod end with a much smaller mesh and measure the fish that have escaped through into the smaller mesh. So, how is selectivity used to adjust fish measurement counts? Let's bring back our length frequency distribution collected by the scientists. This shows the lengths of fish that were brought onto the boat by the Danish seine net. Now we overlay selectivity and we can see that only 50% of 30 centimetre tiger flathead are caught by the net. If only 50% are caught, then it means the real population is double that. So we double it. For fish of 28 centimetres, you can see that only 25% get caught. The real population then must be 4 times this. We can do this for fish of all sizes, and what we end up with is a good understanding of the fish population length frequency. So, that's about it for availability and selectivity. Just to recap, in this section we've covered the availability of fish to fishing gear and the effect of selectivity on the information that scientists collect. In our next section, we'll be looking at the importance of fishing logbooks for helping scientists measure changes in fish populations.